I'm Won Lee. Today's topic is point estimation. Let's take a little review about terminology. Okay, uh, estimator, statistic obtained from the sample. This sample is what? Theoretical sample, right? And estimate is just the value of estimator calculated from the real value, small x1, x2, xn. So those two different terminology and some more unbiasedness, efficiency, and consistency. Okay, so I think you understand what those terminology mean. Finally, x bar sample mean x bar is best estimator of mu. S square is this divided by degrees of freedom is the best estimator of sigma square. Sigma square is a population variance. Okay? Okay, let's go to point estimation. There are two types of estimation, point estimation and interval estimation. Point estimation refers to estimating an unknown value. Unknown value of population is a parameter with a single value, with one value. Whereas, whereas interval estimation refers to estimating the range within which the parameter lies. Okay, let's focus on point estimation here. In previous example, what is it? How long does it take to the summit, right? Estimate the length of time it takes to reach the summit. You might ask several people because of you gather samples, data coming down the mountain because they are experienced individual. When you ask to several people, how long does it take to reach the summit? Then they will answer, and you summarize their answers. These answers are sample. You would like to conclude, estimate. For example, it will take not about 35 minutes. It will take a 35 minutes, just one value. Okay? How about that? 35 minutes, a pinpoint value. In other words, if the time taken to reach the summit is represented by random variable x, you aim to estimate the mean expectation of x. In other words, mean mu, right? Using your sample values obtained. It is reasonable to estimate the time, length of time. As you know, the best point estimator for the population mean mu is x bar. In practice, to point estimate the population mean mu, we need to actual n sample values obtained like small x1, small x2, small xn, right? And to estimate mu using the calculated x bar. Of course, x bar is some value from your sample, sigma xi divided by n. From those sample values is the best approach. That is the best approach because it is best estimator, x bar is best estimator for mu by theory. And actually, it is very natural and rational way. However, with a significantly large number of possible samples, that means their population, X. You can take a sample this way, that way, this way. There are many, many ways to take sample, right? So there are many, many X bars. But you take only one sample, size n, x1, x2, xn. So with a significantly large number of possible samples and corresponding sample means, each sample has its mean, right? How can we estimate mu with a single sample value x bar? It is a question. Is it okay? Let's address this question. Let's see why it is okay to estimate with a single value x bar. As learned earlier, chapter 3, central limit theorem, x bar can be said to follow normal distribution due to central limit theorem. In other words, x bar follows normal distribution with a mean mu variance sigma square over n, right? The variance what is the square root of this variance? Standard deviation, n. That is sigma over square root n. But this denotes standard deviation of x bar. The terminology we use, standard error of x bar. So standard deviation of a statistic, x bar is a statistic, okay, is called standard error. We have to distinguish those two terminologies: standard deviation of random variable x, standard deviation of statistic. That is, we call standard error. We will frequently encounter the term standard error, shortly SE, when conducting statistical analysis with a computer. Statistical analysis, we need a computer, and the computer gives us the result. You may frequently see SE, standard error. So you have to know what this terminology is. Okay, now let's see the graph of x bar here. X bar, random variable x bar, has a distribution. What distribution? Normal distribution. And for this one, okay, the standard error is about like this. This is sigma over square root n. I told you 3. 1/3 of this length is this big. Okay, it is symmetric. So, but if n increases, the spread of distribution of x bar will become narrower. N increases, then this value will be smaller, so the distribution gets narrow like this, right? Understand it? In other words, as n gets larger and larger, then the distribution of x bar becomes more peaked around the center mu, right? It's smaller. And the obtained sample mean estimate x bar, here there are many x bar, okay? Small x bars here. But we get only one x bar. We get only one x bar. There are possible many x bar here, so it's a distribution. But x bar is around here, okay? Obtained sample value x bar will be closer to mu, even though x bar is one of so many possible sample means. All the sample means, okay, let's take another graph, normal distribution like this. Then all the sample means, all possible sample means lie between this area around mu. So n is large enough, very big, then this the width of this normal distribution will be tighter, will be smaller. In extreme case, where n approaches infinity, x bar will coincide with mu. N is infinity means what? The sample size is infinity. Sample size infinity means population, right? So x bar will coincide with mu. And this one infinity, then what? Sigma over square root n goes to 0 as infinity, sigma over infinity, square root infinity, infinity. So goes to 0. In other words, coincide with mu. Therefore, it can be understood that best estimator mu of mu is x bar, and we can determine mu by x bar. Okay? Say limit x bar n infinity, x bar equal to mu. What is this? This is consistency. So you understand that. And S square, sample variance, also has a consistency property. See? All right. I think you may understand easily this part. Okay. Okay. Thank you. Bye.